Hi everyone. So today we're going to continue on 14.6. Today hopefully will be our last video for 14.6. I just want to go over maybe two more example, maybe three more example, depending on how much time we have. So what happened is, what if you don't have an initial condition? Well, then you can still generate the solution to the differential equation by forming some kind of initial constant. So imagine the following. Let y double prime equal to xy prime minus y. Find a Taylor series for the solution of y. Once again, I'm going to ask you to show the first four non-zero term. The first four non-zero term. Okay, so this one didn't have any initial condition to begin with, but because it's a second order differential equation, we can assume the following. We're going to assume that y of 0 gives some kind of constant value c1. And y prime at 0 would give some kind of constant value c2. Oh, I'm sorry. Maybe I should write this. Find the Taylor series for y prime centered at x equal to 0. Show the first four non-zero term of the series. If I didn't give you an initial condition, I do need to tell you where I want you to center your Taylor series. So I'm going to go ahead and tell you to center at 0. So we assume y of 0 equals z1 and y prime of 0 equals z2. So that already gives me 2. So now what I'm going to do is continue on with y double prime. So y double prime at 0 would equal to x, which is 0, times y prime, which is c2, minus y, which is c1. So that comes out to be negative c1. So it's good. It's not 0. So we have 3 terms so far. Now I need the fourth term. So I'm going to do y triple prime and see what happens. So y triple prime would equal to the derivative of y double primes. That means I'm taking the derivative of xy prime minus y. So notice xy prime require product rule to do. So product rule will say xy double prime plus y prime. And then derivative of y is just y prime, so minus y prime. So that actually cancel out and just leave you with xy double prime. And so y triple prime at 0 will actually be 0 times y double prime, which is negative c1. So that just come out to be 0. So that's no good again, because we need non-zero term, and that one is a 0. Is a 0 term. So hopefully the next derivative won't be a problem. So I'm going to do y to the fourth derivative, which is basically the derivative of y triple prime. That is the derivative of xy double prime. So which come out to be, once again, product rule, that's x y triple prime plus y double prime times 1, so which is y double prime. And so if I take the fourth derivative and evaluate 0, I get 0 times 0 plus y double prime, which is negative c1. So that come out to be negative c1, which is good. That's a non-zero term. So now I'm ready to write out my solution. So my Taylor series would be y of x is equal to y of 0, which is c1, plus y prime of 0, which is c2 times x, plus y double prime at 0, which is negative c1 over 2 factorial x squared, plus the third term is 0 over 3 factorial x to the third, plus the fourth term is y to the fourth derivative 0, which is negative c1 over 4 factorial x to the fourth, plus dot dot dot. So obviously this term go to 0. which is the reason why we have to have an extra term. And now I'm going to clean up my answer. So my answer is y of x equal to c1 plus c2x minus c1 over 2x squared minus c1 over 4 factorial, which is 24 x to the fourth plus dot dot dot. And so that would be our answers. And without knowing C1 and C2, we probably unlikely be able to kind of figure out what the answer to this equation is. We could definitely do another problem. Let's see if we can try and try at least maybe 2 more. But since this one only take about 5 minutes each, which is not bad. Let's try this one. This one is actually interesting. So I'm going to let y double prime equal to negative y. And once again, I'm going to give you the initial condition. Y of 0 equal to C1. And y prime at 0 equal to C2. And what I'm going to ask you to do the following. This one is a little specific. By using Taylor series at x equal to 0, show that the solution to this differential equation to this initial value problem is in the form of y equal to c1 cosine x plus c2 sine x. Now, before you even get started, you should immediately recognize that if I do plug in 0 for y, I do get c1. And if I take the derivative of the y prime, and plug in 0, I will get c2. So it satisfies the initial condition. Now the question is, how do I show this is actually the equation? Well, let's do that. So we already know that y of 0 is c1. Actually, you know what? I am going to write it over here. We know that y of 0 is c1, and y prime at 0 is c2. We do know that y double prime is equal to negative y, so therefore y double prime at 0 will just be negative c1. Now, what is y triple prime? Well, y triple prime would actually just equal to negative y prime, because just negative the derivative of y. So therefore, y triple prime at 0 would just equal to negative c2. Then what is y to the fourth derivative? Well, that would actually come out to be negative y double prime, which is basically just y. So therefore, y to the fourth derivative come out to be c1. Now, in case you're wondering how I did that, I simply just take the derivative of both left and right side. That's it. So if I take the derivative of y double prime, I get y triple prime. And then I take the derivative of negative y, which I get negative y prime. And then to get y to the fourth derivative, what I'm going to do is differentiate y triple prime. That means I'm basically differentiating negative y prime. So that forms negative y double prime, which is basically y. Now, it shouldn't be too hard for you to notice a very simple pattern forming, but let's go through a couple more. Y to fifth derivative would basically just be the derivative of y, which is y prime. So y to fifth derivative would be basically what y prime is, which is c2. And y to sixth derivative is y double prime, which is technically equal to negative y. So therefore, y to the sixth derivative at 0 will be just negative c1. And then you can probably guess what the next one's going to be. Is negative y prime. So therefore, y to the seventh derivative is negative c2. And this pattern go on and on forever. So what does that mean to our Taylor series? Well, let's go and form our Taylor series. So if I look at this list correctly, all right, I guess I'll do it on the bottom. Here we go. So then what is y of x equal to? So it would be equal to y of 0, which is c1, plus y prime is 0, which is c2 times x, plus the next derivative is negative c1 over 2 factorial x squared, plus negative c2 over 3 factorial x to the third, plus c1 again to fourth derivative x to 4 factorial x to the fourth, plus c2 over 5 factorial x to the fifth, and then plus negative c1 over 6 factorial x to the 6, plus negative c2 over 7 factorial x to the 7, plus dot dot dot. So if I now do a little bit of organizing, I'm going to go and separate them into two series. One of them only involves C1. And then a second series only involves C2. And then what I'm going to do is factor out C1 from the first group with all the C1. Then hopefully you'll recognize that the first series, 1 minus x squared over 2 factorial, plus x to the 4 over 4 factorial, plus x to the 6 over 6 factorial, plus dot dot dot, that actually formed the cosine power series. And this one where I say x minus x to the third over 3 factorial, plus x to the fifth over 5 factorial, and minus x to the 7 over 7 factorial, so on, that is actually the sine series. So therefore, it did come out to be y of x, did come out to be just equal to c1 cosine x plus c2 sine x. So I think that's pretty neat. So maybe we'll do one more example and that would be it. So it would be a relatively short video. Hopefully I finished before 20 minutes. How about this one? Find the first 3 non-zero terms for the Taylor series of y of x at x equal to 0 if y of x and its derivatives satisfy y prime equal to y squared plus x with y of 0 equal to negative 1. So this one only requires to find the first 3 non-zero term. It is a first order differential equation. We're only given the one initial condition, so that means we have to find 2 more higher order derivative that's non-zero. So I guess we just go for it. So we know that y of 0 equal to negative 1. I know that y prime is equal to y squared plus x. So y prime as 0 would be negative 1 squared plus 0, which is 1. So remember, when they say y of 0 equal to negative 1, that means when x equal to 0, y is negative 1. So therefore, plug in 0 for x and negative 1 for y. So that's pretty good. So now let's do y double prime. So that would be the derivative of y squared plus x. So that would be 2y y prime plus 1. derivative of x is 1. So y double prime as 0 would be 2 times y, which is negative 1, times y prime, which is 1, plus 1. So that come out to be negative 2 plus 1, so it's negative 1. So look like we have the third term. That was easy. I was expecting some of the term to become 0, but I guess that didn't happen. So I can now write out my power series. So y of x is basically equal to y of 0, which is negative 1, plus y prime is 0, which is 1 over 1 factorial, which is 1, times x, plus negative 1 over 2 factorial, x squared, plus dot, dot, dot. Don't forget the plus dot, 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 because you are being asked to write out a Taylor series, which is an infinite series. So therefore, you should have the plus dot, dot, dot to indicate the series continue on forever. And so I can just simply clean up this into y of x equal to negative 1 plus x minus 1 over 2 x squared, plus dot, dot, dot. So that was pretty easy. It took about 3 minutes to complete, which is nice. And I think that's it. That would be the last of 14.6. And we'll continue on 14.7 in our next video. Alright, talk to you guys later. Bye-bye.